So today we're going to do graphing derivatives. So we've practiced finding a derivative and plugging things in. Oh, and let's review. Derivative means slope, specifically of a tangent line. And a tangent line, what does that mean? What does a tangent line mean? Yeah, that's what I always say. Kisses the graph at 1 point. So it comes by and just touches the graph at 1 point. Okay, so now we're going to draw a graph of a derivative function. So you have an original graph, and we're going to do a graph of its derivative, which is kind of cool. It's cool, guys. Neat. Okay, so first vocabulary word here, this is a huge vocabulary word in calculus, is critical point. That is where the derivative is 0 or undefined. And what you're going to do, and sorry, my handwriting is so loopy, where the derivative is 0 or undefined. What you're going to do in your delta math is it's going to ask, where is the derivative 0? Where is the derivative undefined? And you're going to put in like x equals 3 or 5 or, wherever it is. They're going to have a graph for you to look at. I'm just going to draw a few quick sketches. What does it mean to have a slope of 0? What would a 0 slope look like? Yeah, and I'll just act it out. Horizontal. Okay, so there's a few ways that can happen. Your graph can look like this, and you would get a horizontal tangent line like that. Do you see what I'm saying? Comes by, just kisses the graph at that 1 point, but it's horizontal. Your graph could look like this, and you would get a horizontal tangent line like that. Or it can be like a cubic function where it does this, and it actually goes horizontal for that one moment in the middle, but then keeps on going. So it doesn't actually have to turn around. Like usually it does, but it doesn't have to. And then what does an undefined slope look like? Vertical, the other way, right? Like this is 0 slope, undefined would be the other way. So that would be if your graph does something like this, and you get a vertical tangent line in between. The other way a derivative can be undefined is if you have a sharp edge. So like your absolute value function, you can't even draw a tangent line at that point because it's a sharp edge. And we're going to talk a lot more about that next class too, but you can't get a derivative at that point because it's a sharp edge. So it's literally undefined there. Okay. And your critical points are potential locations of relative maximums or minimums. So potential, because it could be a maximum or a minimum, but it might not be. Like, look at the pictures that I drew for you. This is a minimum, this is a maximum, but do you see how there doesn't have to be one? So it's the potential, and then this is huge too. It's the location of, it's the x value. The actual maximum or minimum is the y value. Do you remember how we write them 7 at x equals 3 or whatever it is? You're getting the x value. So it's the location of, because they will mark it wrong in the AP exam if you say that that x value is the maximum. It's the location of the maximum. All right, so if your function is increasing, and this is what we're going to color code, is the increasing and decreasing. If the function is increasing, that means your derivative is positive. And if the function is decreasing, that means your derivative is negative. And this is where I use above sea level and below sea level. Positive means above the x-axis, negative means below. And I'm just going to real quick, like on a sticky note, draw you a picture of what this looks like. Here's a quadratic. You don't have to draw this, just watch so that you can understand what's going on. Okay. Do you see how if I draw a tangent line here, the slope is 0? Okay. Do you see for this part, the graph is increasing? Do you see how if I draw in tangent lines, like that just come by and hit the graph like at 1 point, do you see how they are going up? They have a positive slope. For this portion, the graph is decreasing. Do you see how if I draw in tangent lines, they have a negative slope? Okay, so increasing, positive, decreasing, negative. We're going to color code. So for each of these, we're going to state the critical points, label them as a maximum, minimum. I guess it could be or neither. I should have put or neither in there. And then sketch the graph of the derivative function. So if you are going to color code with me, pick one color to be your increasing and one color to be your decreasing. So for me, I'm going to use orange for increasing and green for decreasing, and just kind of stay consistent with that so you don't mess yourself up. So here's where the graph is increasing. Here's where the graph is decreasing. And where is the critical point? The critical point is at x equals what? 0. Don't ever think that. It's 0. Are you seeing that? Like 0 is where that change happens. Okay, or you could draw in a horizontal tangent line there. So your critical point is 0, and it is a relative maximum minimum. Which one is it for this graph? Minimum. So we're going to say relative minimum at x equals 0, and we're going to sketch the derivative graph. Now I have to give a pep talk whenever I do this. If you are an insane perfectionist, like you need everything to be perfect, you're going to have to take a few deep breaths, because these don't turn out perfect. They turn out good enough. Okay. The only points that we can plot specifically are the critical points. Everything else is good enough. Are you with me? You're going to have to let it go. Okay. So since we have a 0 slope at 0, the only point you can put specifically is 0, 0. That's the only one that you can put on there. Now for this decreasing part, we want to be negative. For this increasing part, we want to be positive. That means you want to be below sea level and then above sea level and go through that point. So it's going to look like this. This is our derivative graph. You want to stay below the x-axis, go through that point, and then be above the x-axis. That's your derivative graph. If you're like, that's it, yep. Let me show you really quick just to do another side example, because that one ended up being at the origin, and I just want to show you it's not always the case. What if we moved this parabola over a little bit? Like, what if I put that center at 3? Do you see what I'm saying there? Okay, then on your derivative graph, you would have a point right there at 3, and it would look like this. Do you see, like, if I moved it over? Okay, because I don't want people to always think it's going to be the origin. It's just because that one was centered at the origin. Go ahead.
So now it's opposite for when you're doing derivative graphs. So like you go right through, you go instead, you go left.
Oh, I just made that up. Yeah, no, I just invented that. Usually you have a graph to look at. Okay. All right, so looking at this one, I'm going to label my increasing parts orange and my decreasing part green. And again, that's optional. If you don't want to color code, if you're like, I don't want to do that, that's fine. I just think it helps to visualize, especially while you're just learning this. Like, this is the first time you're seeing this topic. Until you get the hang of it, color coding helps. So there are actually 2 critical points, places where you have a slope of 0 for your tangent line. So where's the first one? Yeah, I would. Well, yeah, this one's at 1. Can I go left to right just to stay organized? So this one's at -2. Are we seeing that? All right, relative maximum or relative minimum? Max. Okay, so we're going to say relative maximum at x equals -2. And then we have relative minimum at x equals 1. So when you go to graph your derivative, those are the only 2 points that you can plot specifically. The rest of it is going to be like, it's good enough. Okay, so like you have to sort of let that go. So where we have a 0 slope is at -2 and +1. So do you see how I put those points on? They're zeros. They're on the x-axis. Those are like on sea level. Those are like at sea level points, because the slope is 0 there. And so what we want to do, this part's increasing. We want to be positive and then negative and then positive again. So we want to be above, then below, then above. Are you following me there? Okay, and then go through these 2 points. So watch, we want to stay above the x-axis, go through that point, go below, go through this point, and then be above again. So it's above, below, above, because it's increasing, decreasing, increasing. Are you seeing that? Are we making some connections there? Go ahead.
So it doesn't matter how it how it does it.
I don't know how far down this goes or any of that. These are the only 2 points we get specifically. So the rest of it, you just have to be like, it's good enough. Okay.
Positive, negative, positive, imaginary things, is that really color them?
Oh yeah. Number line. You know what? We're going to do number lines eventually in this class too. So I'm glad you're thinking about that. All right. So I'm going to color code. Increasing is going to be my orange color. And then decreasing is going to be my green color. Try and stay consistent with whatever you picked though, because if you start making them backwards, you're going to confuse yourself. Let's list out the critical points. And I want to see if you get them all. What have we got?
And
Good. That's the one I was kind of worried about. Do you see how -2, there is a 0 slope there? So we would say neither at x equals -2. And then what else?
Maximum at 1.
Good. Relative maximum at 1. And then the last one, yep, relative minimum at x equals 3. So when we go to graph our derivative, those are the only 3 points we will graph specifically. The rest of it will be like good enough. Okay, so if you even want to go ahead and put those, you're going to have zeros at -2 and 1 and 3. Again, those are like the at sea level points. Like the slope is 0 there. And I even drew in the horizontal tangent line, so you can see that the slope is 0 there. And then you just go above or below based on what you're supposed to do. Now this one's a little tricky because I threw a neither one in there, so watch. We're going to be above, and then above again, stay above, and then below, and then above. So watch me draw it. We're going to be above the x-axis, above sea level, get to that point, stay above, good, and we call that a bounce, until I get to this point, and then we're going to be below for in between these two, and then above again. How far up does this go? No idea. How far down does this go? No clue. I kind of like this, it's sort of like doodling in math class. Does this remind you of the polynomial functions where does it bounce or does it? Yeah, it's kind of like that. All right, what type of graph is this? It's the value. Okay, so my increasing part is going to be orange. Decreasing is going to be green if you feel like color coding. There is a critical point. 0. So we have a relative minimum at x equals 0. However, can I draw in a horizontal tangent line there? No. So when we go to graph our derivative, there will be no points on there to start out with. We'll draw it. I'll get you there, but hold on a second. You can't put that on there because you can't draw in a 0 tangent line. So you can't put any of those at sea level points. All right. Now we want to be below and then above. But you actually can get these specifically because we know the slope of these. If it's linear, you can get a slope. What is the slope of this portion? Down 1. So that's -1. And then the slope of this portion is, okay, watch me draw this and then you can do it. So we're going to be at -1 until we get to 0. And then we're going to be at +1 from then after. Do you remember these graphs when we were doing limits? I introduced them when we do limits from the left and right, because that is a graph of a derivative of absolute value. I like to introduce it early. Let me throw this in here as a side problem. Just look real quick. Let's say your absolute value graph got stretched. Do you remember vertical stretched by 2? Remember something like this? Do you see how I'm making it like narrower? Now what's the slope on each side? 2 and -2. So its derivative graph would look like this. What about, I love doing what about questions. I'm going to use up all my sticky notes. What about if it looked like this? Then what?
One. Oh, no, yes.
Move it to the left too, and it would look like that. Cool? Cool. It's neat, guys. Neat. All right, number 11. What is this a graph of? Which parent function is that? Exponential. This is my favorite one. All right, it is increasing all the time. So there are no critical points. Bless you. Bless you. And so we will again get to put nothing on our derivative graph. And also, since it's increasing all the time, we are going to be positive or above sea level all the time. So watch, this is really cool. Here's the derivative graph. You ready? The derivative of an exponential is an exponential. It's itself. Thank you. Which is cool. It's just the coolest graph. All right, so I love that one. It's itself. When we start doing all the derivative rules and stuff, e to the x is the, here, I'll teach you this one right now. What's the derivative of e to the x? E to the x. Isn't that great? It's itself. It feels like you didn't do anything. All right, and then this last one. What is that the graph of? Actually, let me ask you that. How do you know it's signs? Starts at 0. Okay, so I'm gonna label my increasing part orange and my decreasing parts green, which is showing up kind of like as yellow on there. Now, this is gonna have an infinite number of critical points. Do you see what I'm saying? The plus whatever n, yeah, it's gonna be fun, right? Because it's cyclic, it's gonna keep waving forever. So we're gonna have a relative maximum at x equals, and the way you write this is you do the first one, and then you do plus however often they happen. So where's the first maximum? This one right here. Yeah, pi over 2. Plus, and it's gonna happen each time you go around the unit circle. So what is one full cycle around the unit circle? So plus 2 pi n. So every time you go around, you get another one. No one ever really likes that, and I get it because it looks weird, but you're just adding once around the circle. And then relative minimum, again, there's an infinite number of them. Where is the first one? And when I say the first one, it has to be the first positive one. It's 3 pi over 2. And again, you have to go around the circle to get the next one. So there's an infinite number of critical points. So when we go over here, I'm not going to go but so far. And these are labeled by pi over 2 if you want to label like the first couple of tick marks. Just each tick mark is pi over 2. And so the only points you can plot real specifically are those critical points. So where we have the horizontal tangent lines over here. So we're going to have negative 3 pi over 2, negative pi over 2, positive pi over 2, 3 pi over 2. Every other tick mark is going to get a point. And again, those are your at sea level values. Those are the zeros, where you have a 0 slope, a horizontal tangent line. And so we're going to be below and then above, and then below and then above, and then below and then above, forever and ever and ever and ever and ever. So watch. This first section is going to be below, and then we're going to be above, and then below, and then it's going to be above, and it's going to keep doing that forever and ever. And so what I want you to make a connection about is that what's the derivative of sine? Cosine. Isn't that cool? All right, and then we're gonna like do one question here to pull it all together. What happens to the degree of a polynomial when you take a derivative? Can I bring you back to this side real quick? When we had a quadratic, bless you, the derivative ended up being linear. When we had something that was cubic, this is to the third, the derivative was quadratic. So what happens to the degree each time you take a derivative? You subtract 1. And so I want you to list out derivative of cubic is going to be quadratic. We're going to make the list real quick. Derivative of quadratic would be linear. And what would be the derivative of something linear?
Constant.
Good, constant. So that's the order it goes up.